Now we're going to take a look at finding the area under normal curves when we are dealing with a sample average. So we're going to take the central limit theorem into account to help us out here. So whenever you have a sample average, the standard deviation of the distribution of these averages is not going to be the standard deviation that they give you, but instead you're going to have to calculate a new one. So what you'll do is you'll take your original standard deviation that they give you and divide it by the square root of n. And n is your sample size. So you divide it by the square root of your sample size to get the standard deviation of the mean, or x bar. So easiest to learn this through example. Let's hop in. We have a standardized test here. The mean score is 600 and the standard deviation is 40. But remember, we said that was the original standard deviation. Now we want to change that. So we're going to take 40 and we're going to divide it by the square root of whatever the sample size is in the upcoming problem. So imagine a random sample of 25 people took this test. Their scores were averaged together to get 620. What proportion of samples are that high or higher? Well, our number here, 25. So our sample size is 25. We're going to take our original standard deviation up here, and we're going to divide that by the square root of n. And n we got from our problem, our random sample of 25. So our new standard deviation here is going to be equal to 40 divided by, well, square root of 25 is 5. So that's going to come out to a new standard deviation of 8. Now, in this problem, it came out cleanly. In most problems, you'll end up using your calculator and you'll get a messy decimal. So don't expect it to be this nice every time. Their scores were averaged together to get 620. What proportion of samples are that high or higher? Well, if we go ahead and use our new standard deviation for our picture, we can label our markings here. So we have 600. Next one's going to be 608 because we're going up one standard deviation using the new number, not the old one. And then 616 and so forth, and we can go the other direction. So average daily is 620. Well, 620 is going to be about halfway between the second and third marking here. So their scores were average. What proportion of samples are that high or higher? We're looking at the area under this little sliver of the curve, so something very, very small. Let's go ahead and get ourselves an exact z-score, and then we can crank this out. If we know that z-score is going to be equal to the x value that we're interested in, the 620, minus the mean, which is 600, divided by the standard deviation, which is now 8, we're going to have 20 divided by 8, which will come out to be 2.5. So our z-score is 2.5. What proportion are that high or higher? We're going to have to use the normal CDF function in our calculator. And our left bound, our left side of our shaded region, is going to be that 2.5 right here for our z-score. That's the left side. And then on the right side, we're going to go to positive infinity. So we'll just put in 1,000 and call that good for our purposes. So we go to second bars, normal CDF, 2.5, comma 1,000. That'll give us the area under that little sliver of the curve. Now, if we're getting an area of 0.006, that's very small. Our picture confirms that it's very small. So what proportion of samples are that high or higher? 0.006 would be the answer to this problem. 0.006. So that's less than 1% would be this high or higher. We're going to do a very similar problem, and this time we're going to talk a little bit more about what this information actually tells us, why we would ever care about something like the area under the curve. So we're looking at IQ. We have a mean score of 100 and a starting standard deviation of 15. But if we look at our problem, it says the average score of the 33 people in class was 107. So the 33 people in class is our sample size. So we're going to calculate ourselves a new standard deviation by taking the one that we started with, the 15, and dividing by the square root of our sample size n, which is going to be 33. So 15 divided by 33, we're going to need our calculators for that. Square root of 33, excuse me. And we're going to get approximately 2.611. I'm going to write that down. And that's our new standard deviation that we calculated. So we're looking at our normal curve. I'm just going to get some rough numbers in here. One standard deviation up from the mean of 100 is going to be 102.6, we'll say. And then one more up from that is going to be 105.2 approximately. Those are just estimates. And then one more standard deviation up from there is going to be 107.8 roughly. So the average score was 107. So 107 is somewhere very close down on this end. What proportion of samples are that high or higher? So we're shading to the right. Based on this, do you think a statistics class is a representative sample of the population? Well, we're going to have to find the area under the curve first. So the area under the curve we can clearly tell is going to be very small, even smaller than the last one. But we do need a z-score before we can continue. So let's calculate our z-score. It's going to be the x value. So the x value is 107. We're going to subtract our mean of 100. And we're going to divide by our standard deviation that we just got of 2.611. So we take out our calculators. And our numerator here is going to be 7. Our denominator will be the number we just calculated. So we keep it exact in my calculator here. We're going to get approximately a z-score of 2.681. 2.681. So that's our z-score. Now we need to find the area under the curve. So we're going to use normal CDF. And our left end here is going to be our z-score, 2.681. And our right end, we're going up once again, so that's going to go to positive infinity. So we'll just pick a large number like 1,000. Back to our trusty calculator. Second bars, go down to normal CDF, 2.681, comma, 1,000. That will give us our area, which is going to be about 0.004 if we round it. So based on this, do you think that a statistics class is a representative sample of the population? There is a 0.004 probability, about a little less than a 0.5% chance that randomness would make this occur. That this is something you would expect, and randomness just produced the result. So yes, it's absolutely possible that this is a representative sample, and we just happen to get a lot of people with very high IQ scores grouped together. However, it's much, much, much more likely that there's something special about a statistics class. Perhaps it attracts people who happen to have a higher IQ, especially if you're thinking about a college class or an upper-level college class, a graduate class. The people that make it to that level of education that are taking those courses probably have a very high IQ, much higher than the average person in the population. So whenever you see things that are that unlikely, you can't rule out the fact that it's chance completely, but you can say it seems more likely that there's something else going on. And we'll talk about specific things like this, how we run tests and what probability, what threshold is good enough to make a statement.